Okay, so welcome to this next video in which we are discussing entropy and the second law of thermodynamics. Okay, so in the previous video what we did is we defined entropy and we used this example of dropping a drop of red dye into a beaker of water and it dispersing out into the beaker of water to motivate this understanding. Okay, and we know that, of course, from basic experience that if you have a beaker of water where the red dye has distributed itself homogeneously among the water molecules, it will never then return to a single drop that is at a single position in the beaker of water. Okay, and we came to the understanding that the reason for this is that the system has a huge number of equally likely microstates, and what we mean by that is the system contains a huge number of water molecules and it contains a huge number of red dye molecules. Each of these water molecules has a certain set position within the beaker, and each of the red dye molecules has a certain set position and orientation within that beaker. Okay, you have a huge number of possible ways that you could rearrange all of those water molecules and all of those red dye molecules within the system. Okay, every last one of those is a plausible microstate that the system could exist in. Okay, so that's the collection of absolutely all microstates. Now, we don't see the microstates. We are humans. We are a macroscopic organism. What we see is macrostates, okay? So we can see, for instance, that the drop of red dye is at one point in the beaker. We can see that the red dye has distributed homogeneously within the beaker of water, okay? These are two macrostates that the system can be in that we can see. Okay, now for each of these macrostates, each of those macrostates has an entropy, and the entropy of that macrostate means how many microstates that the system could exist in. Of all the microstates that the system could exist in, which we've just discussed, how many of them would look like this to a macroscopic organism such as a human. That is what is meant by the entropy of this macrostate. Okay, similarly you can calculate this entropy for this macrostate here where the red dye has distributed homogeneously within the beaker of water. Okay, and basically the reason that it always goes from being in this macrostate to being in this macrostate is that the entropy, the number of microstates which would all look like this macrostate, is absolutely phenomenally higher than the entropy of this macrostate here. Okay, so just the sheer probability that the system will adopt a microstate that has this as a macrostate is much, much higher than the probability that the system will adopt a microstate which has this as its macrostate. And that is why we always see red dye molecule, well, we always see the droplet of the red dye distributing out and never the opposite process. Okay, so basically people often say that entropy always goes up, okay, that entropy increases, and this is almost true. In fact, what is true, but it needs to be said more carefully, basically. And I want to now show you an example of why this needs to be said more carefully. But before we do that, we need to consider entropy of solids, liquids, and gases. So which system will have the, well, which macrostate will have the higher entropy? Okay, so basically, if we consider solid water, okay, so solid water is a macrostate. Solid, liquid, and gas, these are macrostates. These are things that humans can understand. We can see the difference between ice, we can see the difference between water as a liquid, and we can see water as a gas as well. Well, we can see steam, certainly. Okay, so those are the macrostates, and what we now need to consider is which of those macrostates has the greatest entropy. Okay, so let's have a container here. So let's say this is some glass container here. And let's say it contains water molecules. Okay, and these water molecules can exist in these three different states: solid, liquid, and gas. Okay, and these are macrostates, so the human can see it. The human can look at this container and see whether the water is in the solid, the liquid, or the gas. So let's discuss which macrostate has the highest entropy. Well, basically, if it's a solid, you know, all of the water molecules will be very close together, like so. Okay, and they'll all be at the bottom of the container, so they won't be occupying much of the container, you know, they'll all be like so. Okay, and basically there's not much movement there, so how much entropy do you think that the solid has? Well, basically the number of microstates of the system that would all look like this, that would all appear to have the macrostate of solid to a human, that's going to be much, much lower than if we look at the liquid case, where they can adopt a much greater number of conformations, basically. Okay? So if we now look at the liquid case here, so they're all more spaced out, a little bit more spaced out, and there are a much greater number, basically, of microstates for this system that would all look like a liquid, basically, that would all have the macrostate of a liquid. Okay, and then finally, as a gas, the number of microstates of the system that would all appear as gases to a human is far greater still, basically. So this leaves the problem, basically, because why does ice freeze? Okay, because we do see ice freeze, and yet we've just discussed that the number of possible microstates that would appear as frozen to the human is much lower than the number of possible microstates that would appear as a gas to a human, for instance. Okay, so that doesn't seem to obey our logical intuition that, you know, you're always more likely to see a macrostate that is more probabilistic because it has a greater number of microstates that would look like that. But we do see ice freezing, so this is the problem, basically. So what I'm now going to state is the second law of thermodynamics, which will come to the rescue here. Okay, and I'm going to go on to a new piece of paper for this, because it is, after all, very important. So, this is now the second law of thermodynamics. It's given a huge, great, pompous title, but I suppose it deserves it. The second law of thermodynamics. And basically, the second law of thermodynamics says that in any spontaneous change, the entropy of the universe always goes up. Okay, so often just abbreviated to the entropy of the universe always goes up. Okay, so basically, if you look at the macroscopic state, or the macrostate of the entire universe, you will always find that the macrostate of the universe, the entropy of that macrostate goes up. As time progresses on, the entropy of the entire macrostate of the universe always goes up. The entropy of the universe always goes up. Okay, and this might seem totally undoable, basically. It might seem totally, well, how can we work with that at all if we're having to always think about the rest of the universe? But it's actually not too difficult. There's a way that we can simplify this down. Okay, so the entropy of the universe always goes up. Okay, so in order to get some sort of a grasp of how to work with this law, we need to have the concept of a system and the surroundings. Okay, so basically, let's take our system here, okay, which is the system in which we will be doing chemical reactions. So let's call this the system here. And then the rest of the universe around it that is outside of the system, we'll call that the surroundings, basically. Okay, so you have a system, and then outside you have the surroundings. Okay, so in the system we will be doing a chemical reaction, and basically we can calculate the change in entropy that will occur within the system. Okay, so basically, if we have a chemical reaction occurring in here, and we'll take the example that we had earlier on, where we had ammonia gas added to hydrogen chloride gas and turning into ammonium chloride. Okay, so NH4Cl, which was a solid. Okay, so we have in this system ammonia molecules and hydrogen chloride molecules. They're reacting to produce this solid ammonium chloride. Okay, so the macrostate is changing. The human can see this. We're mixing two gases, okay, and we're forming this white cloudy powder basically. So the macrostate is changing. Okay, we can take the macrostate of that at the end of the chemical reaction, okay, which is that we've got all this white powder, and then we can look at the macrostate at the start of the reaction, which is that we had the ammonia gas and the hydrogen chloride gas. And we can say, what's the difference in the entropy, basically? How many microstates of this system look like this, and how many microstates look like that? And this is where it gets a little bit more complicated than just the water molecules and the red dye molecules mixed in together, because of course we've got chemical reactions now occurring. Okay, so let's draw a picture here again, because it will help. Okay, so this time the molecules aren't unbreakable, basically. In the water and the red dye, we were just thinking about the molecules of water as one blue dot which couldn't be broken apart, and the red dye molecules as one red dye molecule which couldn't be broken apart. Now what we're going to have to consider is the ammonia molecules. We'll have to consider those as a nitrogen atom with 3 hydrogen atoms stuck onto it here, okay, like so. And we'll have to think of the hydrogen chloride atoms as a chloride atom with a hydrogen atom stuck onto it as well. Okay, like so. And we've got all of these, and of course you can now rearrange the hydrogen atoms and the chlorine atoms. You can break them apart. So now when we consider all the microstates of our system, we have to consider the hydrogen atoms as separate entities, the chlorine atoms as separate entities, the nitrogen atoms as separate entities. So you can therefore calculate all of the different microstates that this system can be in. So you need to specify where every single hydrogen atom is, where every single nitrogen atom is, where every single chlorine atom is. Okay, and if we calculate how many of those microstates would have this system basically as a white powder on the floor, where you have chlorine atoms, so what's going to happen is it's going to go to this sort of a macrostate, well, this sort of a microstate in fact, where you have, here's the chlorine atom, and then you have the nitrogen atom in blue here, with the hydrogen atoms coming off it. 1, 2, 3, 4. Okay, so this is the ammonium chloride here. Okay, so basically we need to work out how many microstates are there of the system which would all look like a white powder on the floor of ammonium chloride, and how many microstates are there which would have ammonia molecules and hydrogen chloride molecules. Okay, so we need to work out how many microstates of this system all look like this macrostate where we've got these two gases, and how many microstates all look like this macrostate where we've got a white powder. Okay, and what you will find is that there are far more macrostates that actually look like this. Sorry, far more microstates that actually look like this macrostate than look like this. So the entropy actually goes down in this reaction. So this is another one which doesn't make sense if we're not thinking correctly in terms of the second law of thermodynamics. Okay, so basically what we would call this is we'd call this the change in entropy of the system. Okay, now delta means change, S, remember, is what we called entropy, and because this is happening within the system, we call it system down here. So all this means is the entropy of this macrostate, so the number of microstates which would all look like the formation of ammonium chloride macrostate, okay, and we'll call the entropy of this start over here, where we had ammonia gas mixed with hydrogen chloride gas. Let's call this S1, and let's call this S2. So basically the change in the entropy of the system will be how much has the entropy changed. So it will be the after entropy, take away the starting entropy. This is how much the entropy is going to change when we go from the start to the end. Okay, so this is the change in entropy associated with our change in macrostate, which we know is going to happen. Okay, and this is going to end up being negative. Entropy has gone down. Okay, but what do we also know about this reaction? It releases a lot of heat, okay? And what you can imagine is all of the heat being given off from the system and going into the surroundings. Now, this is where we have to make entropy even more complicated than we previously discussed. We've had the first complication where we've had to think about molecules actually being broken apart and you changing the constituent pieces, okay? Now, the next complication is that entropy actually also includes all the possible orientations and all the possible ways of ascribing energy to the molecules. Okay, so basically, if you really want to think about what the microstate of a system is, okay, this is what you really need to specify in order to specify the microstate of a system. You need to tell me where absolutely every fundamental particle that you have in this system is, basically. So position of all the fundamental particles, and those are the particles which can't be broken apart. And you also need to tell me what their energy is and what their velocity is, i.e. which direction they're moving. Now, of course, we're thinking very classically here. Thermodynamics is a classical theory, okay? It's not a quantum theory. I do not know that much quantum mechanics, so we're not going to, well, I'm not able to take this into quantum mechanical domains, okay? So we will think of particles having a position and, you know, an energy, basically, and a velocity as well. Of course, quantum mechanics says that you can't know both of those at the same time, but we'll go with it because this is a classical theory. Okay, so remember, all science is just models. This is a model. It may not be the best model that we currently have, but it is a model. Okay, so to specify a microstate, you need to tell me the position of every single particle in this system, and you also need to tell me the energy and the direction of motion. Okay, so that creates a huge number of different microstates, okay, because not only can you reposition all the molecules, you can also reascribe the amount of energy that you're going to give to each of them and change the direction in which they're going to move. So there are an absolutely huge number of microstates. Okay, now really what entropy of a macrostate is it still remains the definition that I've given you. It's the number of microstates which would all have that macroscopic appearance, basically. Okay, so how many microstates that the system could exist in actually would appear like that when you look at them macroscopically. Okay, so that's what entropy of a macrostate is. Okay, so basically when you release heat from the system into the surroundings, what is heat? Heat is energy, so you are putting energy into the surroundings. Now the surroundings also has a microstate. It also has, you know, loads and loads of fundamental particles which all have a position and a velocity. Okay, now if you're adding more energy in, then you now have a much greater number of possible microstates, basically. Okay, because when you give energy out into the surroundings, the energy can now be ascribed to particles, and therefore the total number of microstates that you can have is far greater, because if you've got more energy, then you've got more possible different ways that you can ascribe the energy. Okay, so if you give out more energy, then the total number of ways of ascribing energy to different particles is going to be greater, okay, because you've got more energy to ascribe. Okay, so that means that the entropy of whatever state the universe is currently in is going to go up, because there are now going to be more microstates that correspond to that macrostate because there are more microstates fundamentally, basically. The total number of microstates that the surroundings could exist in has gone up, and therefore whatever macrostate it's currently in, the number of microstates that are going to correspond to that will also go up. So basically, giving out heat into the surroundings is going to increase the entropy of the surroundings. So basically, when you take into account the change in entropy of the universe, you need to work out the entropy, the change in entropy of the system. Okay, so it's going to be equal to the change in entropy of the system, and it's also, you're also going to have to take into account the change in entropy of the surroundings. Okay, so here's surroundings. And basically, the reason that this reaction can occur, the reason that ammonia can react with hydrogen chloride to produce ammonium chloride, is that even though the entropy of the system is actually going to go down, so this number is going to be negative, because it gives out so much heat which will go into the surroundings, you're actually going to increase the entropy of the surroundings great enough that means that the entropy of the change in entropy to the whole universe, because this process occurred, is actually still going to be positive. So the second law of thermodynamics basically says that this number is always greater than or equal to 0. Okay, right. And in the next video, what we'll explore more is why, when you give out heat to the surroundings, that leads to an increase in the entropy of the surroundings.